Now, on this problem, I want to find the resultant moment of these two forces added together. Now, in general, it would probably be better to add those forces together, find the resultant force, and then just do a single cross product of the resultant force since they're at the same point. However, I want to show you that a little trick on this. So um, we're going to do them separately. So we're going to find the moment about point O. I'm just going to add together all of my R cross Fs. Okay. And what I want to prove to you is that for FB here, you can take the position vector from point O to anywhere along the line of action of the force. So I can either do that R vector or this R vector. And in fact, I could do this R vector too if I wanted to, but that's probably not as easy. Okay, so you can go from the point to anywhere along the line of action of the force, and you're going to want to choose the one that makes your life the easiest. Okay, but for this one, we're going to go through both pieces. So we'll do it first from O to A. Okay, so R from O to A is nothing more than 6K. Okay, uh, R from O to B is just 2.5J. Okay, and again, this is from point O to anywhere along the line of action of the force. Now, before I get too far, I should probably write my force in Cartesian form. This is actually FB, excuse me. Okay, so I'm going to take that 780, and again, it's just two dimensions that I've got here, right? So my R vector of the force B going from A to B now, I need that position vector. None of that is in the X direction. 2.5 of it is in the J direction, and -6 of it is in the K direction. Now keep in mind, this is the force, okay, of that 780. So my R vector here is from A to B. So this is different than the moment arm, OA or OB. So this is going from A to B. And then I divide that by the square root of 2.5 squared plus 6 squared. From that, I find that force B to be 300J, okay, minus 720K. So that's that force of B, writing that 780 Newton force in Cartesian form. Now, I want to show you that whether or not I take ROA cross FB or ROB cross FB, I'm going to get the same answer to prove to you that I can go from the point to anywhere along the line of action of the force. So when I go RA to B, I'm going to have that 6K, and all I have to do is take that times the J, right? Because K cross K is 0. So I've got K cross J, and again, that if you want the, right, going this way around the circle is positive, this way around the circle is negative. So if I'm going K cross J, I'm going K cross J equals I. I'm going negative around that force. Okay, so that's going to be negative, and that's going to be in the I direction. So that becomes negative 1800 I. That is the moment of force B about point O. Now I can do the same thing, but use the 2.5J. And again, J cross J is 0. So now I'm just going to do J cross K, and I'm going to get 2.5 times 720. Okay, and this is J cross negative K, so I go J, K, I. So this time I'm going positive around this circle. However, I have this negative, positive and negative gives me a negative, so I get negative 1800 I, which is the exact same answer as I had before. Now keep in mind, what does this relate to? Well, this relates to a vector in that direction, but now this is a moment vector, so it's actually a rotational vector. So what I have is a rotation where my thumb of my right hand points in the negative x direction. It's that rotation that I've got right here. That would be, negative 1800 I. That's the moment vector of force B about point O. It creates it about the negative x-axis. So that's what that moment actually tells me. Also recognize I can sum the moment from point O to anywhere along the line of action of the force. So because of that idea, when I do the same thing for force C, I recognize that I can either go from O to A or O to C. Well, O to A is a much simpler vector, which makes my cross product much easier. So I'm going to use from O to A to find that force. And it's always easiest to choose the simplest vector to do the cross product, because cross products can be a little tedious. But before I do that, I need to find the force of C, which is just going to be the 420, okay, times 2I minus 3J minus 6K divided by 2 squared plus 3 squared plus 6 squared. Square root of that is 7. Okay? If you don't believe me, go ahead and try on your own. So that force written in Cartesian form, which we've done before, is as follows. 120I minus 180J minus 360K. Now, I'm going to use that 6K and cross it times that vector to find the moment of force C, essentially, which is going to be ROA crossed with FC. So I take K cross I, 6 times 120, and I'll let you figure this out on your own, but that's going to be a positive J. Okay, and then I'll have K cross J, 6 times 180. That's K cross negative J. Okay, that becomes plus I. So again, I'm going K cross negative J, K, J, I. That's where the I comes from. This one's going negative around. Okay, but I have the negative over here, so that two negatives become positive. And from that, I get the moment to be equal to 1080I. Oops, not 1800, 1080I plus 720J. Now to find the resultant, I just add those two together. So again, I'm going to take this guy, add them together to get my resultant moment, and I just get negative 720I plus 720J. So what that looks like on my plot, again, remember this is a moment vector, okay? So that's basically the direction my thumb would point on my right hand. My fingers curl around that vector, right? So it's going, negative in this direction, positive in the J direction. So that resultant force of this whole thing would be pointing in that direction. This is my resultant moment. And again, it has a rotation to it. So those two moments of those two forces added together give me a moment in that direction of the rotation of my curling fingers around my